Tengan todos muy buenos días. Antes de iniciar con este gran evento que nos reúne hoy aquí en el Tecnológico de Costa Rica, observemos el protocolo de seguridad de este Centro de las Artes.
Ante la eventualidad de una emergencia, le invitamos a seguir las siguientes recomendaciones de seguridad. Siga las instrucciones del moderador. Evite obstruir las vías de tránsito con sus pertenencias. Evite el uso de teléfonos para que se encuentren libres y se puedan atender llamadas de emergencia. Aléjese de ventanales y puertas de vidrio. En caso de que suceda un sismo fuerte, proteja su cabeza y espalda colocándose debajo de la butaca o bien agachándose y cubriéndose la cabeza con los brazos. Este centro cuenta con 4 salidas de emergencia. Observe desde su asiento el círculo de color ubicado en el respaldo de la butaca justo delante suyo. Este color indica la puerta por la que usted debe salir en caso de una eventual evacuación de las instalaciones. Quienes se encuentran en el escenario y en camerinos deberán salir por la puerta ubicada al lado derecho del escenario. Cuando se dé la señal de desalojo, diríjase a la salida que le corresponde en forma rápida, ordenada, manteniendo silencio total y sin devolverse a recoger objetos personales. Una vez afuera, diríjase a la cancha de fútbol y espere recibir instrucciones por parte de la Comisión Institucional de Emergencias o las autoridades de la institución. Las personas heridas, golpeadas o afectadas como consecuencia de la emergencia deben dirigirse a los integrantes de la Brigada de Primeros Auxilios para que reciban asistencia. Absténgase de hacer bromas o comentarios infundados y/o exagerados que aumenten la tensión provocada en el evento. Colabore en labores de rescate o combate de incendios si posee capacitación y se siente preparado psicológicamente para hacerlo. El Tecnológico de Costa Rica les desea una estadía grata y segura.
Muy buenos días a todos.
Good morning to all.
Tecnológico de Costa Rica,
an institution dedicated to education, culture, and technology in Costa Rica, would like to welcome you. Today, we are still celebrating our 45th year anniversary, and we will witness new progress in Costa Rican science. Tecnológico de Costa Rica today turns our country into the first Latin American nation to do a high-temperature plasma discharge using a device that is unique in the region, a stellarator. Authorities from the Academy and the state, special guests, national and international press, and a series of scientists around the world are following this wonderful event. The main purpose of this research is to turn plasma into an alternate source of energy in the future. Academia researchers have offered the country these results so that they can be used in whatever is relevant to the development of Costa Rica. In order to achieve this first discharge, the Laboratory of Plasmas for Fusion Energy and Applications of TEC has operated the experimental device for plasma confinement at high temperatures called Stellarator de Costa Rica 1, known as SCR-1. As part of this event, we will be connected this morning in 3 different sites. The first one being Princeton University in the United States. From there, we have our main lead researcher, Dr. Iván Vargas. He is in an internship at Princeton. He is the general director of the plasma laboratory at Tech. The second site where we will be conducting this event is here at this art center. And here we have Engineer Irene Cañas, Minister of Environment and Energy, Julio César Calvo, Rector of Tecnológico de Costa Rica, and Paola Vega, Vice Rector of Research and Outreach of Tecnológico de Costa Rica. In addition, we have with us institutional authorities, congressmen, special guests from the socio-productive sector, family members of the researchers and students at the Plasma Laboratory, the press, students, and officials of Tecnológico de Costa Rica. The third site will be precisely the Laboratory of Plasmas for Fusion Energy and Applications of TEC. This is precisely where we'll have the high-temperature plasma discharge. Today, you will be able to witness the discharge in 4.5 seconds. This will be production of plasma, which is the fourth state of matter. And you will see a flash of light. This will be precisely plasma, which is in most of the visible universe. You might ask yourselves, why such a short time? Well, let me tell you, in order to produce this fourth state of matter here on Earth, we have had to do research for 6 years and create a device that is capable of producing plasma. So we ask you to be alert so that you can see this great event that will last, again, 4.5 seconds. This project is the result in plasma physics that has been most complex in the history of Costa Rica. For reasons of space and safety, we cannot all be at the laboratory for the discharge, but we will be able to see it on the screen. At the laboratory, we have the engineering coordinator for the laboratory, Engineer Jaime Mora, together with other people that are involved in this wonderful project. We also want to greet this morning all of you that are with us around the world through the website www.tech.ac.cr. To formally begin with this event, we ask you to stand for the national anthem of Costa Rica. You may take your seats. We will go now to Lisette Castro, who is at the Laboratory of Plasmas for Fusion Energy and Applications of TEC. She will tell us what is going to happen there. Good morning, Lisette.
Buenos días, Johnny. Un
Good morning, Johnny. This is great news for the entire world. Today, we will witness a historical event in our countries. We are at the plasma laboratory of the Tecnológico de Costa Rica, and Costa Rica, again today, gives a giant step in development. As was said before, we will have the first high-temperature plasma discharge in a stellarator. It is unique to it is one in Latin. In the world have them, and Costa Rica is one of them. This was developed in Costa Rica, and it combined, and the idea is to reproduce the energy produced by stars through a process called fusion. Tech researchers will inject hydrogen gas atoms into the device in order to convert it into plasma. Atoms are ionized and electrons are separated from the nuclei of the atoms at temperatures higher than 300,000 degrees Celsius. This temperature is equivalent to standing on the surface of the sun. And as we have said before, we are proud to say that this is the first time that a high-temperature plasma discharge will be conducted. We have several researchers. Engineer Jaime Mora is the director of the process and the protocol for starting up this. Let us begin with the checklist for the accelerator. Let us begin by verifying that it is turned on at 24 volts and 2 amps. We have verified that it is on, no alarms. The controller is also on. Verify that the wave is on. Well, let us go back to the Art Center while they complete the checklist. Thank you, Lisette, for your information from the laboratory. We will go back to her shortly for more information. And we will continue from the event at the Art Center. And in an insert on the screen, you will be able to follow what is going on at the laboratory. With you now, we have a message from Julio César Calvo, rector of the Tecnológico de Costa Rica. Good morning, Minister of Minay, Irene Cañas, congressmen that have joined us today, Vice Rector of Research of Tecnológico, Paola Vega, Coordinator of the Plasma Coordinator, Ivan Vargas, who is at Princeton University and who's watching this through our streaming capabilities, the students of the lab, authorities and officials of the Tecnológico, communication media, and let me greet all people that in different parts of the world are watching us live through the internet. First of all, let me welcome you and thank you for your presence at Tecnológico to celebrate not only the discharge in the stellarator, but also the 45th anniversary of Tecnológico. It is a great source of pride to be able to share the results of several years of intense research in the study of plasma physics. For Tech, this has been part of our strategy, and we have given it great priority. We are minutes away from seeing the first public discharge of high-temperature discharge of plasma generated from our laboratory. Tech today will allow us to see plasma created in a device developed thanks to the research of this group of Costa Rican scientists in the Laboratory of Plasmas for Fusion and Application of Tech. It is through this laboratory that we want to do world-class research in fusion as an alternate source of energy and the use of plasma in industrial sector through the training of highly qualified human resources and with the development of high technology national equipment. So today, at international level, our institution continues to contribute to the development of the country. We are training human talent and a critical mass for the creation of this knowledge. Once again, our public universities have shown how teaching and research in higher education are fostering the development of this country in new fields of knowledge, creating opportunities for innovation, entrepreneurship, and the establishment of high technology industries in Costa Rica. This country opted for basing its development model on knowledge, and the tech will continue to contribute in order to have a better country for all. Today, I want to highlight the work done by Dr. Ivan Vargas, coordinator of the laboratory, who, together with the researchers and students, have been able to position us at international level within this field of knowledge. Ivan is living testimony of the Costa Rican model. In here, we have demonstrated that investing in education is the best tool for social mobility, for solving the problems that we face, and the best strategy to face the challenges of the future. Ivan graduated from school in Aguasarcas. He studied physics at University of Costa Rica and was a tech until he got his PhD before he went to Universidad Complutense de Madrid. Many other Costa Ricans have also made progress in knowledge, arts, and sports, and these examples should inspire many young people and are the best result of the country model that we follow and that we can continue to improve. Our thanks to Ivan and his team, thanks to the country for giving us the importance of having quality higher education. Today here, we have built tomorrow's Costa Rica. Thank you very much for attending. Following, we have Engineer Irene Callas, Minister of Environment and Energy. Good morning, Dr. Julio César Calvo, Rector of Tecnológico de Costa Rica, Paola Vega, Vice Rector of Research and Outreach. Warm greetings to the congresspersons, teachers, researchers, students, and family members of our research and students who have joined us today. First of all, I would like to apologize for the minister. Don Nectar had this event in his agenda for several weeks. However, he was called to a meeting of ministers of environment of Central America and is in Honduras. When you are acting minister, as I am today, it is something that sometimes you have to face difficult situations. However, sometimes you get almost a prize, like is the case today, which is being here on such an important day. I would like to give you a very brief message. On August 9th, 1884, Costa Rica was the third city in the world of having electric light, after New York and Paris. We were the third city in the world to have electric power. Costa Rica at this time has an electricity coverage of 99.4%. Last year, we generated over 99% of an energy from renewable sources. We're a small country, but we are among the big ones. We're small, but we really carry our weight. And today, we are here again, placing ourselves among the big guys. placing ourselves next to large powers and becoming #1 in Latin America. I believe that this is truly one day that should make us proud to be Costa Ricans. And again, we are flying this flag of going ahead. In 2014, when the administration began, we took on a significant challenge of having a national energy plan that would be participatory with the different sectors of the country: education, consumers, producers, environment. And finally, last year, we made the 7th National Energy Plan official. The main axis of this plan is a low-emission economy, an economy where we are going to reduce and continue to reduce emissions from fossil fuels, so much so in electric production as well as in transportation and fuels. At COP21, Costa Rica reaffirmed this commitment. Costa Rica reaffirmed that we are one more of the 194 countries that agreed to remove carbon from the economies. Why do I say this? Because the step we're taking today no doubt goes in that direction. Today, when we push that button, we will be pointing toward the development of plasma as an alternate energy source, a clean energy source that is in tune with what was decided by the sectors in energy matters in these countries. This is in agreement to what we accepted at COP21. Let me also say, and I imagine not all of you are familiar with it, but these are the objectives that were approved in September of last year by the United Nations. These are the Sustainable Development Objectives. There are 17 of them. Since I became familiar with them, I carry them with me, because to me, these are almost like the 10 Commandments. If we want to have an agenda for the future, we all have to work on these objectives. The objective number 7 is accessible energy that does not pollute, clean energy. And one of the objectives that is a new one within this new version for United Nations is number 17. And although it is the last one, to me it is one of the most important. Goal number 17 says alliances to achieve sustainable development. What Tecnológico is doing today is very important for all of our society. And the alliances we need to continue, and the partnerships we need to build will include education, production, and all other sectors so that we can all move towards a low-emission, sustainable economy. And this is something that we all have to do together. Today, I want to congratulate Dr. Iván Vargas for this great initiative and for this great work. I will also want to congratulate Tecnológico. And I want to promote that you continue. I want to give you incentives to continue researching and to continue finding solutions for this Costa Rica that we want to continue building day after day, a sustainable Costa Rica, a Costa Rica that is responsible with the environment. And I hope that we can continue walking along the path of renewable energy so that we can all be proud of having contributed our grain of sand in order to accomplish the sustainability we deserve for future generations. Thank you very much. Princeton University in the United States and the Max Planck Institute in Germany have joined us for this very wonderful event. First of all, we were here from the experts at the Plasma Physics Laboratory from Dr. David Gates, Chief of Accelerators, and George Nelson, Director of Advanced Projects, Dr. Michael Sistor, Assistant Research Director, and Stuart Bryan, General Director. In addition, from the Max Planck Institute in Germany, we have Dr. Robert Groth, Director of the Accelerator Optimization Department. With you now, the messages from these international experts.
My name is David Gates. I'm the head of accelerator physics here at the Princeton Plasma Physics Lab. Dr. Vargas and I met originally in Germany, underscoring what Hutch Nielsen just said about the importance of international collaboration. I lead a collaboration on the Wendelstein 7X accelerator in Germany. And in fact, start of your experiment in Costa Rica is really timely because the Wendelstein 7X accelerator is the largest accelerator ever built in the world. And there's a great deal of excitement that has come as a result of the onset of that experiment. We welcome Costa Rica to the international collaborative world of accelerator physics. And we're very excited about continuing a collaboration between our two institutes. In particular, there's a lot of excitement about the opportunity to design accelerators in the modern world. And we have a great deal of computational capability that we've been able to bring to bear. And we think it really provides an excellent opportunity for the development of fusion energy in the near future. And once again, congratulations on the startup of your new device.
We're at a moment in the history of fusion development where international collaboration is more important than ever. The scientific and technical challenges of fusion are such that we need to pool our talents and our capabilities in order to bring about fusion energy as soon as possible. Clearly, the TEC recognizes this, already having established important international collaborations with fusion centers in Germany and Spain in bringing the SCR stellarator to reality. And in so doing, they are moving into the fastest growing area of international fusion research and leading the way in Latin America. We've also collaborated with the University of Wisconsin in the US and bringing a Tokamak into the same laboratory. We at the Princeton Plasma Physics Laboratory are pleased to join with Costa Rica and with TEC as a collaborator in fusion energy, and to be able to work with Dr. Vargas programs on these two important care of him here at Princeton and TEC in the Republic of Costa Rica for this important event.
I just wanted to extend our congratulations to Costa Rica and to the Institute for Technology on your starting up of the new experiment, the Costa Rica accelerator, and of your experiments on Medusa, the spherical tokamak. And we really welcome you to actually accelerator research and research in compact configurations. And we're delighted that you've chosen these two configurations because we are also focused on these approaches to fusion research, which we think are the most promising experimentally. In particular, we're delighted that you actually have chosen a compact accelerator, and you now have the smallest aspect ratio and the most compact accelerator in the world, which is really exciting. And we look forward to collaborating with you and on your future results, which we think will be quite interesting. Thank you very much, and good luck.
On behalf of the Plasma Physics Laboratory here, I'd like to congratulate the Instituto Tecnológico de Costa Rica in starting this wonderful new experiment in fusion research. Fusion research, as we all appreciate, is critical to the future of how humankind will generate energy in the 21st century. It is also a fantastic challenge in science and engineering, so it is a perfect topic for your university, and we're very thrilled to welcome the contribution to the future of your university. We are pleased also that it's part of a started a few years ago. Also, I'd like to congratulate your government for making the wise decision to be the pioneering country in Central America to enter into this field. This field requires the best brains in the world, and it's all rooted in strong collaboration among nations, and we look forward to collaborating with you in the future. Our laboratory here is also dedicated to fusion energy and plasma science. We are also keenly interested and working on the concepts that you are beginning research in, both the stellarator and the spherical tokamak that you started a couple of years ago. So we welcome you. We hope to collaborate with you in the future. We welcome exchanges between our two institutes, and most of all, we wish you the best of luck in this new endeavor.
Fusion is not only a promising possibility for a new primary energy source, but fusion research is also an exciting research field combining many interesting areas ranging from fundamental physics problems to challenging engineering developments. On behalf of the Max Planck Institute for Plasma Physics and also speaking for the IEA Stellarator Heliotron Collaboration Program, I would like to congratulate you to the successful implementation of a stellarator now joining the worldwide community with a new device. Although more difficult to design and build and also more complex regarding its confinement properties, stellarators are a promising alternative to tokamaks. The main advantage is that they provide steady-state confinement of a hot fusion plasma. At a time when optimized superconducting stellarator Wendelstein 7X here in Greifswald in the northeast of Germany produced its first plasma, it is great news to see that also in other places of the world stellarator research is gathering momentum. If we want to understand the details of stellarator confinement and find out which is the best way to go forward, we have to explore the configurational space of different stellarators. Here, compact, innovative stellarators such as the stellarator of Costa Rica 1 will play an important role. The new device in Costa Rica will also help to foster scientific collaborations. In fact, already a student from Costa Rica is working on his PhD thesis in Greifswald. We are certainly looking forward to extending international collaborations which form the basis of the worldwide fusion endeavor and which are absolutely necessary to educate the young generation for the future tasks to come. We congratulate you on this achievement and we are looking forward to first scientific results and exciting discussions.
We thank our international experts for their kind words. We will go back to Princeton University now, where we have the General Director of the Plasma Laboratory of DC, Iván Vargas. He will give a presentation called Plasma as the Future Source of Energy. We welcome Iván Vargas. Today is a truly wonderful day for us where we tell the national and international community about this device. This is a device that is unique in Latin America and one of the few in Latin America destined to investigation as a future source of energy. Today, I am at the Plasma Physics Laboratory in Princeton, where I have activities linked to research projects that we have in our country. Allow me, first of all, and as briefly as possible, to tell you about the various aspects related to the work that we develop and which we present to you today. Our day-to-day is surrounded by technology that requires ever more energy. So where do we get this energy? In the particular case of Costa Rica, we have hydropower, wind power, geothermal power plants, just to mention a few. The question that we can ask is whether through these energy sources we will be able to meet the demand for the future. And the answer is no. Projections tell us that every day we will need to have more energy and that the current options that we have will not be able to cover the demand. So the question that we could ask is, what other energy source could we use? What we need to do is to look to the stars. These stars are constituted by plasma, which is the fourth state of matter, where electrons and nuclei of atoms have been unlinked, and they are in some kind of soup where their behavior is very different from when they're in a solid or gas state. Stars in this plasma state are able to conduct processes called nuclear fusion. And basically, the idea is that they join light nuclei, producing heavier nuclei and releasing a large amount of energy. To produce nuclear fusion, we need to link atomic nuclei that have a positive charge. We all know that charges, that equal charges, repel each other. Therefore, we need to give them sufficient kinetic energy so that they can close to each other in order to achieve the interaction of nuclear forces, giving rise to the process of fusion. How much energy could we produce with this source? To give you an example, with 1 gram, we would be able to produce 26,000 kilowatt hours. This is the energy that is required by about 80 houses in our country, Costa Rica, to be powered for 1 month. Or another example would be 1 gram, which is equal to the energy produced by 2,400 gallons of oil. What are the advantages of this energy source? Well, first of all, it must be very clear that it is universal. In other words, all stars in our universe, in our visible universe, produce their energy through a fusion process. In addition to that, it is safe, it is environmentally friendly, and it is conservation friendly, as it does not generate any impact with the gases. It is unlimited because the fuel that is used can be found in water and in some salts within the Earth's crust. It is a source of energy of industrial scale. In other words, it would be able to produce enough energy for entire cities 24 hours a day. It is also an is used in different manners because it is a process that has already been accomplished in laboratories around the world. And also, we need to realize that it's the future because it will revolutionize the way in which human beings produce energy. How do we achieve fusion on Earth? Clearly, we cannot generate the intense gravitational fields as stars do to confine these particles. So what we have to do is to take advantage of the fact that plasma is constituted by positively and negatively charged particles, and they interact with magnetic fields. In other words, if we expose these particles to intense magnetic fields, we will be able to have them define their trajectory. In the example I'm showing here, we're interested in not losing the particles at the extremes once we have directed them in a particular direction. So what we do is to fold this cylinder that you see in order to have a toroidal shape. Particles then are confined, are trapped, and in order to generate this intense magnetic field, what we do is to use coils, depicted here in green. Particles then, what they will do is to go round and round around this geometric shape, and what we will do is to heat this plasma, continuously heated, in order to have a fusion of the particle. This process, and where research is being going on, we have the Tokamak. Tokamak is a Russian word that means toroidal chamber with coils. The jet is in the United Kingdom. The Tokamak concept has different variables. You have more compact devices whose plasma has the shape of an apple, and they're called spherical tokamaks. We know that they reduce some of the instabilities, and they allow freezing plasma at lower values of the magnetic field. We have different spherical tokamaks, just to mention a few. We have the NSTXU at the Plasma Physics Laboratory in Princeton University in the United States, the MAST Tokamak in the United Kingdom, and the Medusa CR Tokamak in Costa Rica, donated by the University of Wisconsin at Madison in 2013. In the Tokamak devices, we have already been able to achieve nuclear fusion processes. In 1991, the JET was able to produce about 1 megawatt of fusion power, and in 1994, the TFTR in the physics laboratory in Princeton has produced about 10. After that, in 1997, the JET was able to produce 15 megawatts fusion power, and to date, we have different research activities that are focusing of several countries. Has been estimated to be about 500 megawatt output power, considering that the input power will be about 50 megawatts. This device is currently being built in Cadarache, France, as you can see in the photograph in the lower right. It's for electric production following this process. These reactors are fed with deuterium, which is an isotope of hydrogen that we can find in water, and lithium. This is an element that we can find in some salts in the Earth's crust. Plasma would be generated inside the device, and the energy released would be used through a heat exchanger that would take it to a steam generator, a turbine connected to a generator, and thus the production of electricity. The residue is helium gas, which we know has no environmental impact and actually has some industrial uses. There are other ways to do this. There are other devices that allow the same process. You can see here in the illustration on the left the principle for the operation of tokamaks. It has the disadvantage that in order to confine plasma, you need to create high currents within the plasma that generate some instability that sometimes turn off the plasma. Other research has been done in other types of devices that would not require circulating currents, but actually the confining magnetic field would be generated based on external coils. The disadvantage, however, is that when doing this, the coils have a more complex geometry. These devices are called stellarators, from stella and generator, which in Spanish we could say means stellar generator. The stellarator was a concept invented by Lyman Spitzer Jr. in 1951, and in 1953, in what today is the Princeton Plasma Physics Lab, the first stellarator in the world was built. Around the world and through the years that have gone by since 1953, we have seen the construction of different stellarators. In the particular case of the Costa Rica 1 stellarator, it is in the category of a modular stellarator. And at this time, it is one of the close to 10 stellarators that are currently operating around the world. And we must say that only 6 countries have a device of this type. The SCR-1 stellarator in Costa Rica took a long process for design, construction, and implementation. In the design stage, we needed to develop codes that would allow us, first of all, to calculate the magnetic field with the modular coils, the shape of the plasma, as you can see on the right-hand side, and the subsequently because it was accelerated at CEC. Well, first of all, we need to train the human resources in fusion technology and physics, plasma physics, because in turn, this will allow us to collaborate with international research centers in the pursuit of this alternative energy. With this, we will also strengthen the participation of Latin America in fusion research. And in the particular case of the accelerator, this will allow us to identify any problems related to the design and construction of small modular accelerators. I should highlight that one of the great advantages of having small devices is that it allows you to explore configurations, it allows you to explore and research fusion engineering and fusion physics without having to invest hundreds of millions of dollars, as can be done with some other large devices. In the particular case of Tecnológico de Costa Rica, we have two magnetic confinement devices, a spherical Tokamak, donated, as I said before, by the University of Wisconsin and Madison, and Accelerator of Costa Rica 1, which is the one that we are introducing today. I should note that around the world, again, there's only 3 institutions that have both a accelerator and a spherical Tokamak, and Tecnológico de Costa Rica is one of them, of course. Allow me now to show you very briefly some of the stages that led us to the construction of this device. In here, you can see the construction of the vacuum vessel, both the internal as well as the internal features. You can see the internal surface of the device with the different windows, which we call ports, access ports, to hook up research equipment. This is the final result once the ports were soldered onto the chamber. And then we proceeded to build the modular coils, which is perhaps one of the most complex parts because of their shape. We first used a 3D printer, then we did shapes, and this was then soldered onto the chamber in the positions that had been previously defined using special equipment for this. The final result is the modular accelerator, as you can see, with close to 24 access ports for scientific equipment to research plasma. Accelerator of Costa Rica has peripheral systems, including an industrial battery bank that feeds the modular coils. This, in turn, is regulated by a current controller. We also have a vacuum pumping system, which precisely what it does is to extract the air from the device, and a gas injection system that allows us to input hydrogen, which will be ionized and converted into plasma. All systems are operated in a controlled manner through a specific system. And at the same time, we have diagnostics to investigate plasma. The heating system, I show it here in more detail, was previously simulated, then it was designed and implemented. It is a system that is based on microwaves. As I said before, we designed diagnostics. These are pieces of equipment to investigate plasma. This one, we call it, well, it is a Langmuir probe, and it allows us to measure the density of the temperature of plasma. This has been proudly tested in our lab. And these photographs that you see at the bottom are precisely the measurements that we have been able to take from the plasma generated in our lab, except in here, these are low-temperature plasmas. We also designed a microwave heterodyne interferometer, the same as the other peripheral system, we did through first simulation, then design and implementation plasma, and also the density of the plasma. In general, Accelerator of Costa Rica 1 is a very complex device. A lot of complex technology was used. It is a device that, in my opinion, would be equivalent to the project for technological development for physics research that is the most complex ever carried out in a day. That, from my point of view, should be recorded in history, not only of our country, but also of all of Latin America, since we were able to operate the first stellarator in Costa Rica. Finally, I would like to express my thanks to different institutions and people. First of all, Dr. Vicente Queral from Centro de Investigaciones, CIEMAT, in Spain, to all researchers of CIEMAT who advised us in the very long process of designing our device. My special thanks to all of my colleagues of the Max Planck Institute Plasma Physics Division, who also actively collaborated and advised us on the various aspects, including Bert Hollander, Director of Theory, Dr. Michael Berblack, Dr. Luken Baxon, and Dr. Matthias Otte. To all of them, our thanks for all of the support and all of the assistance you provided us in developing this device. Also, I would like to thank Dr. Horacio Fernandez from the Plasma and Fusion Institute in Portugal for all of the collaboration provided, specifically for designing the current regulator. Thank you very much to all of you, and I hope you enjoy the first high-temperature plasma discharge of Stellarator of Costa Rica 1. Thank you very much. We thank Dr. Iván Vargas for this presentation. And the time has come to witness how Tecnológico de Costa Rica turns our country into the first nation in Latin America to have a high-temperature plasma discharge in a device that is unique in the region. We will link again with the plasma laboratory, where we have our colleague Lisette Castro. Go ahead, Lisette. Thank you very much, Johnny. As you said, we're back at the plasma laboratory so that in a few minutes we can look at this very important event. Let's mention some of the benefits of plasma. 98% of the visible universe is times more electricity than a hydropower plant. It can power 80 houses for a month. The role of tech is to do the research that will be executed by others in order to generate electricity. We're a few minutes away, 5 seconds, a great step in science. This has been done thanks to the dream, to an idea that began in the heart of Costa Rican scientists. We just saw him, Iván Vargas. He is a great representative of our country. And Costa Ricans have looked to this project. In this project, it is good to know that the rest of Dr. Vargas's team used to be students. And today, these people you are seeing here on screen are students that graduate already as engineers from TEC. They are the ones doing the research that will impact the life of all Costa Ricans. The most important part in this part of the research is not fusion itself, but actually to control the plasma and understand its behavior. And as we were told, conventional energies in the future will not be enough to supply the energy required in future decades. That is why it is so important to do research in this type of devices in order to generate energy in the future. Jaime, we're very close to the discharge, aren't we? Yes, we will clear the area for safety reasons. Only operational personnel will remain. Perfect. Deactivate the EMO. Deactivated. You can now proceed to the button. Thank you, Lisette, for that information. We should add that what we'll see in a few minutes will be 4.5 seconds, which have been the results of 6 years of research at Tecnológico de Costa Rica. Please be alert to the screen, because this will be filmed by the camera that is close to the stellarator. What you will see will be plasma, the fourth state of matter, a flash that means great progress for Costa Rican science. The most important part in this research, again, is not to have fusion for many hours, but actually to control plasma and study its behavior. So, let us proceed now to pushing the button to initiate the high-temperature plasma discharge. Once the button is pushed, 10 seconds later, you'll have the discharge. Therefore, I invite all of you to help us in the countdown for these 10 seconds. For this, let us invite then Engineer Irene Cañas, Acting Minister of Environment and Energy, the Rector of Tecnológico of Costa Rica, Julio César Calvo, and Dr. Paola Vegas, Vice Rector of Research and Outreach, to push the button so that we can begin with the discharge. Go ahead, please. We start with the countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You can see the images, the emotions over at the laboratory. This is truly a historical event in Costa Rica. This is the first high-temperature discharge of plasma in Costa Rica. And there's a standing ovation. Today, June 29, 2016. It's a great step for science in Costa Rica. And this is the first nation to do so in Latin America. After seeing such a relevant event for science in Costa Rica, that shows the great talent we have in Costa Rica, the researchers of the laboratory will be coming to the auditorium so that you can meet them, greet them, and congratulate them in person. This is, as we said, a great achievement for science under the command of Dr. Iván Vargas. And let's look at the discharge in slow motion again. And as we said before, the most important part in this stage of the investigation is not to have fusion and have it last for many hours, just to control plasma and study its behavior. Germany was the last nation to start its stellarator in February of this year. Now in June we do so in Costa Rica. We now have with us the entire team of the Plasma Laboratory. Obviously you are recognizing them. Congratulations to everyone that participated in this wonderful event. In this way, we have concluded this ceremony to commemorate this great step in Costa Rica. Thank you very much to all of you, both here at the auditorium as well as around the world, thanks to the event being streamed. We are very proud of being Costa Rican. We are very proud of being a small country with great talent, as you can see from these researchers. And thank you very much again.